Hi, welcome back to Physics Teacher, the channel that prepares you for the high school math, chemistry, and physics contests from Waterloo University. This is a question from the Fermat contest, which is the grade 11 math contest. Give it a try, and I'll be right back with the solution. Alright, so this question is question number 24 of 25. It's the second last question and it is quite challenging. It says, for a pair of real numbers a and b that is chosen at random under this condition, what is the probability that these two curves will intersect? So let's start by looking at when those curves will intersect by setting their equations equal. So we can have ax squared plus 2bx minus a equals x squared. And if we just rearrange this by bringing x squared to the other side and factor out your x squared, you'll have a minus 1 x squared plus 2bx minus a equals 0. And so right now you can see if a equals 1, then this x squared term disappears and you'll get a linear equation. And there'll definitely be a solution for that as long as b does not equal 0. But if we do have a quadratic, then we can solve it using the quadratic equation, but more importantly, we want to look at the discriminant. Because if the discriminant is going to be positive, then we know there's going to be a real solution and therefore they intersect. So the discriminant would be 2b squared, so that's b coefficient right here, minus 4ac, your a coefficient being a minus 1, and your c coefficient being minus a. So that is going to have to be greater than or equal to 0 to have a real solution. Alright, so let's expand and simplify this a bit. So here we're going to have 4b squared minus 4 times, if we expand these two brackets, we'll get negative a squared plus a. And that must be greater than or equal to 0. Continuing, we would have 4b squared. And if we distribute the negative 4, we get plus 4a squared minus 4a is greater than or equal to 0. So now what I'm going to do is divide everything by 4. And I'm going to place my terms with a first because I want to work with them next. So I'll have a squared minus a plus b squared. And that's going to be greater than or equal to 0. So let's work with this now. I'm going to make some space. Alright, so first I'm going to add a quarter to each side. Essentially what I want to do is complete the square, but there's a specific square I want to complete here. So that's going to be greater than or equal to 1/4. Now this a, I'm going to multiply by 2 and divide by 2, so I'm not changing anything there. So I'm going to have minus 2a times a half plus, and 1/4 is just a 1/2 squared, and then I still have this b squared greater than or equal to 1/4. Alright, so there's a perfect square there. So I can rewrite that as a minus a half squared, and then I still have this plus b squared must be greater than or equal to, and instead of a half I can write that as instead of a quarter I can write that as 1/2 squared. Now this looks very similar to this condition here, so I'm going to write that condition over here. We have a squared plus b squared is less than or equal to a quarter. Now if I were to write these as x's and y's instead of a's and b's, what they do is they describe circles. So let me write this as an equation, not an inequality, but an equation. So if I had x minus a half squared plus y squared is equal to 1/2 squared, this represents a circle with a center at the coordinate 1/2 and 0 with a radius of 1/2. This one over here, if I rewrite this one as x squared plus y squared is equal to, and again, instead of a quarter, I can write that as 1/2 squared. So this one represents a circle with the center at 0, 0, with the exact same radius of 1/2. So if I were to plot these circles, it would look like this over here. Now let's go back to the inequalities. So this inequality says that we're looking for a region outside of this circle. So here's the circle here. We're looking for a region outside of that circle. And this inequality, which is less than or equal to 1/2 squared, is looking for a region inside the circle. So here's this circle inside the circle. So what we're looking for is a region outside of this circle and inside of this circle. So I've represented that with the shaded area here. So we can rephrase the question then. And the question would be, if we were to choose some random coordinate AB with that condition, and that condition being inside of this circle, what is the probability that it'll end up inside the shaded area of that circle? Or what fraction of this entire circle is shaded? So let's work with that. So the area of the circle is just going to be pi r squared, where we know r for both circles is 1/2. Now let's take a look at this diagram. So essentially what I want to do to figure out the area of the shaded portion, I could figure out the area of the unshaded portion and then subtract that from the circle. Now one thing to note is that this point B is the center of that second circle here. And that second circle goes through the center of this circle right there at O. Then over here at A is where they intersect on their edges. Now OB and OA, you can see, is equal to the radius of this circle. So this radius will equal OA, and it will also equal OB. But not only that, but if we look at this other circle with the center of the coordinate 1/2 and 0, AB is its radius, and its radius is the same, 1/2. So AB is also equal to 1/2. So if we look at this triangle, that triangle has all sides equal to 1/2. It's an equilateral triangle, and therefore all of its angles will be equal to 60 degrees. So what I want to look at first is just the portion that is above the x-axis, and we're going to look at this portion here, this part of the triangle, which is a 60 degrees, and we're going to include that curvilinear space outside of the triangle. So that's almost the entire area of the unshaded region above the x-axis. We're just missing this curvilinear space there. Now, since 60 degrees is equal to 1/6 of an entire circle, 1/6 of 360 degrees, we can say the area inside of this red portion that I've drawn there is 1/6 pi r squared. Next, I can do the same thing here, which will include this portion, this curvilinear area outside of this triangle, and I would come up with the same result. That area is also 1/6 pi r squared. So what I can conclude then is this entire area above the axis is equal to the area of this triangle, plus this little curvilinear space here outside the triangle, and this little curvilinear space here outside of this triangle on the left and the right. Now the curvilinear space on either side, that area would be equal to, for example, the green one would be equal to that area of that portion of the whole circle minus the area of the triangle itself. Let's call that K for now. So that means this portion here is 1/3 pi r squared minus K, and also this portion here is the same. So I can figure out what the area of both of them is just by multiplying that by 2. And then if I add the area of the triangle itself, I get the area of the unshaded portion above the x-axis. And simplifying this by distributing the two will give us 1/3 pi r squared minus k. Now if I want the area of the entire unshaded area above and below, because the symmetry, the portion below is the same as the portion above, so I'd multiply it by 2. Right? So it would become the area of unshaded, or in this case, the part that I shaded in blue, is equal to 2 times all of this. So you're going to get 2/3 pi r squared minus 2k. Therefore, we can now figure out what the area of this gray shaded location is. So we'll call that the area of the shaded. Area of shaded is going to be the area of this entire circle, which we know is pi r squared, minus the area of this unshaded, or the blue portion, which we just figured out to be 2/3 pi r squared minus 2k. And that'll simplify to 1/3 pi r squared plus 2k. Now we need to figure out what that k actually is. So remember that k was the area of the triangle, and it is an equilateral triangle where all sides are going to be equal to r. And you can split that into 2, where this is 1/2 r. And you can just figure out the area of a triangle, which is 1/2 the base, which is 1/2 r, times the height, which you can use from the Pythagorean theorem as just the square root of r squared minus 1/2 r squared, which is 1/4 r squared. So this simplifies to 1/4 r times the square root of 3/4 r squared, or simply root 3 over 8 r squared. And then multiplying by 2 to make sure we get both sides, both halves of that triangle, we get the total area to be k as root 3 over 4 r squared. So we can substitute that into the area of the shaded, and we get the area of the shaded to be 1/3 pi r squared plus 2 times this, which reduces to root 3 over 2 r squared. So now we can figure out what fraction of this shaded area is of the total circle. So our fraction, or our probability, which is what we're trying to look for, is equal to the area of the shaded over the area of that total circle, which is pi r squared. And this can reduce to 1/3 pi plus root 3 over 2 all over pi. So all the r squares can cancel. And you can plug that in your calculator, or you can further reduce it using the common denominator as a 6. So we have 2 pi plus 3 root 3 over 6 pi, which is approximately equal to 0.609, or 61%. So our answer is E.